Discrete optimization, MIP, part 3. Okay, so what we're going to see today is cutting planes. Okay, so the basic idea is like in constraint programming. What you want to do is you want to add new constraints to the system that's going to make the system easier to solve. Now, in constraint programming, you would do that for actually improving constraint propagation and reducing the search space. Okay, so here, what we're going to do is add new constraints. But these new constraints, the goal is to actually improve the linear relaxation, make it, move up as much as you can. Okay, and so these are cutting planes. Okay, I'm going to talk about them this lecture and the next lecture. Okay, and this lecture is going to be focused on Gomory cuts, which are very interesting cuts, as you will see in a moment. Okay, so the basic key idea here of this lecture, very simple. We want to find a new linear constraint, okay, that is valid. That means it doesn't remove any integer solution, okay, any feasible solution. And it helps, okay, which basically means that when you are at a particular point, okay, it's going to remove the value of the linear relaxation, the current basic feasible solution, okay. So it's going to improve the value of the linear relaxation. Okay, so this is what we want to do. Okay, so in terms of constraint programming, this would be okay. I want something that a new constraint which is valid, same definition, and which improve propagation. Here is going to be improving the linear relaxation, which means removing the current value of the linear removing the current optimal solution of the linear relaxation. Okay, so let me illustrate that first geometrically, and then we'll move to the algebraic part and come back to the geometry at the same time. Okay, so this is a very simple MIP. Actually, it's pretty boring. Okay, you'll see, but it's going to be simple enough such that we can actually show these things in practice. Okay, so we are maximizing x2 subject to these two constraints. So 3x1 plus 2x2 is smaller than 6. Smaller equal, and then minus 3x1 plus 2x2 is smaller than 0. Okay, both variables are integers. Okay, so this is the linear relaxation there, right? So obviously it's fractional. x2 is 1.5, x1 is 1. Okay, so x1 is fine. Okay, but this is the relaxation. Okay, now when we are actually trying to solve this as a MIP, the feasible point are this guy, and that guy. So essentially the linear relaxation, is actually having a larger space than the space of all the integer points. And that's where the problems come from, okay? And so what we want to do is to say, ooh, can I improve this relaxation to get closer to these, integer points, okay? So this is one of the cuts that we will generate, okay? So this cut is basically saying that x2 is smaller or equal to 1, okay? And so what this cut is basically doing is cutting this big part on the top of the linear relaxation, and it can do that because we are not removing any integer solution to to the set of constraints, okay? And then we get this smaller polytope now, and we can re-optimize over it. The linear relaxation is going to do its work and get to one of these vertices, okay, which is going to be optimal for the linear relaxation at this point, okay? Find vertices, okay, the value of x2 is equal to 1, but the value of x1 in this particular case is 2/3, so it's still not, it's still fractional, okay? So we're going to generate a new cut. So this is a beautiful cut, right? So look at this cut, all red, okay? And now the value of the objective function, we are cutting another part of this, linear programming space here, the feasible solution to the linear program, okay? And we obtain a smaller polytope, and now the optimal solution, one of the optimal solutions to this linear program is also integral, okay? And if we are lucky enough, the linear relaxation is going to get to this, okay? And then we can stop. Because at this point, we are optimal for the linear relaxation, and both variables have integer value, okay? 1 and 1, okay? So this is essentially the essence of this cutting plane algorithm. You start from the beginning, you start adding these cuts, re-optimizing, adding these cuts, re-optimizing, and you have the optimal solution to the linear relaxation, which is now on a vertex which is all integral. Okay, so there are many ways of generating this cut. Okay, so and what we're going to do today is look at one way, which are these Gomory cuts. Okay, and they are syntactic in the sense that the only thing that we're going to do is look at the tableau and derive the cut from the tableau, the simplex tableau. Okay, the assumption that I'm going to make here. Okay, so I'm going to make a very simple assumption here is that all variables take integer values. These cuts have been generalized by Lawrence, Wolsey, and others for the case where this is not only integer values. There are beautiful results in that area, but I won't talk about this. okay? But they are in, most software these days. Okay, so what I'm going to show you is only make these assumptions because that allows me to, present the cut in a simpler fashion. Okay, so now remember the simplex algorithm is only, dealing with this, basic feasible solution. And remember what a basic feasible solution is. You express some of the basic variables in terms of the non-basic variables. Okay, and obviously these b's here have to be greater or equal to 0. Okay, and in a basic feasible solution, the value of the non-basic variables are going to be all 0, and the value of the basic variables are going to be these b's. Okay, so this is the basic feasible solution. This is the basic feasible solution corresponding to this selection of basic variables and non-basic variables. Okay, so we have this basic solution. Obviously, if all the b's, all the b's are integral, okay, are integer values, then we are great. Okay, so we have a solution, okay, to the MIP. Okay, but in practice, in general, it's not going to be the case. Some of these variables are going to be assigned fractional values. Okay, so we have seen in the previous lecture that this linear programming relaxation is always trying to be cute, right, and making your life as miserable as possible. Okay, and so in a sense here, so some of these values are going to be some of these b's are going to be fractional. Okay, so let's assume for simplicity that b1 is fractional, which basically means that the value assigned to x1 is fractional. Okay, so this is how we can deduce a cut, which is a Gomory cut. Okay, so we'll talk about Gomory later on. Okay, so what we're going to do is we're going to take this row of the tableau. Okay, and the first thing we're going to do is we're going to take these coefficients there and round them downwards. Okay, the largest integer which is the largest integer which is smaller than that value. Okay, and so what we have now, we know that if we round all these coefficients downward, that value is going to be smaller than the value that we have here. Okay, so we can rewrite that constraint as an inequality now, which is smaller than we are smaller or equal to b1 now, but we have rounded all the coefficients downwards, and so all these coefficients now are integer values, right? Okay, so I haven't done anything, right? So this is like self-evident truth, right? So what you see here is essentially a valid inequality that I have, okay? And there is a very interesting property about this, right? So if you look at x1, in a feasible solution, x1 is an integer variable. It has to be an integer, okay? Now this expression here has to be an integer too. Why? Because all these coefficients are integers, okay? And all the xi's are integers, so the whole thing has to be an integer, okay? So now, since you know that this value here is an int, okay? So b1 is a fraction, right? But since this is an int, you can strengthen that constraint and make sure that, and this is still valid in the integer solution to the MIP, okay, the feasible solution to the MIP. We now have that essentially this expression that we had at the beginning, okay, has to be smaller or equal to the floor of b1, which is essentially rounding b1 downwards. Okay, so now this is the Gomory cut. Okay, so what we are doing here is that we are basically taking the coefficients here, okay, rounding them downwards. We are taking the b, rounding it downwards, and of course this becomes an inequality. Okay, and so this is a cut. Okay, now this cut is valid. Obviously, the only thing that I have done are basic, algebraic manipulation, and then exploiting the fact that these values are integers in the solutions to the MIP. Okay, so it's valid, and then it has this other beautiful property that it removes the value, it prunes the basic feasible solutions of the basic feasible solution, which is the optimal value of the linear relaxation. Okay, so why? Well, but look at this thing, right? So in the basic feasible solution, okay, so what we know, okay, is basically that all these non-basic variables have to be 0. Okay, so if the non-basic variables have to be 0, okay, so x1 is going to be assigned to b1, and then the value here, this b1 is going to be obviously greater than the floor of b1, because we assume that b1 was fractional. Okay, so essentially we have this beautiful cut, okay, which is looking at the optimal solution to the linear program, okay, finding a row which is fractional, and then adding a new constraint which remove that basic feasible solution. Now, if I remove that basic feasible solution with that constraint, if I re-optimize, what's going to happen? If I put that constraint in, well, good things are going to happen. So, but before we do that, I want to reformulate this cut. Okay, this is not typically what you do. So this is the cut, but we're going to reformulate it in such a way that it's actually better for numerical stability. And so what we're going to do? So in a linear program, it's very nice if the variables are between 0 and 1, because we typically deal with these things as floating points, and there are as many floating points between 0 and 1 as outside, and outside 0 and 1. So what we are going to do is we're going to take this constraint, okay? So this is the original constraint. We are going to take the cut here, and we are going to subtract one from the other. Okay, and so when we subtract one from the other, you'll see that the x1 is going to disappear, obviously, and then you know, this value is going to be smaller than the other one. So what we get is that we get an inequality in the other direction, where you see here basically the sum of the fractional part of the coefficient times the axis, and then the fractional part of the right-hand side, the b. Okay, so in a sense, think of the Gomory cut now as, I take the tableau and I take the fractional part of all the values, like the basic variables. Okay, I take the fractional part here. Okay, so the value is you know, you basically take, and the fractional part is simply the value, the coefficient minus, you know, the largest integer, which is smaller, the floor of that particular coefficient, and that is to be greater or equal, okay, to the fractional part of the right-hand side. Okay, and that's typically the cut that we're going to use. Okay, and so what are we going to do with this cut? Well, we're going to put it inside the tableau now. Okay, if you want to put it inside the tableau, you have to transform it into an inequality. You take these slack variables that you add. Okay, you re-express that as an inequality. You get s is equal to minus the fractional part of the b1 of that in that tableau. Okay, and then the fractional part of all the other coefficients multiplying the non-basic variables. And obviously, when you look at these constraints, you say, okay, it's not feasible, but that's good. That's what you wanted. You wanted that constraint which is not feasible, otherwise you would stay at the same place. You would still have the same, you know, objective value for the linear, you know, relaxation. But no, so you know that this is not primal feasible, but obviously you turn your head and this is dual feasible. Yes, you re-optimize the dual, and now you get another relaxation, right? And it's a stronger relaxation because you have removed at least one of the bases, right? And so basically that's what you do when you have Gomory cuts. Okay, so you look at the tableau, you optimize the linear relaxation. Okay, so you get this linear relaxation. Okay, then you choose a row where the basic variable is fractional. Okay, so you know that that's not what you want. So you generate the Gomory cut. Okay, the Gomory cut generates this constraint, which is primally infeasible, but it's dual feasible. You use the dual algorithm to re-optimize. Okay, and you have a new value of the relaxation, and you iterate this until, you know, you basically find a solution which is all integral. You know, all the integer values are, you know, all the variables have integer values, or you can show that there are no feasible solution. Okay, so that's the algorithm here for solving MIP integer program using Gomory cuts. Okay. Now, I want to illustrate that so that you can see what it does on the simple example that I've shown you. Okay, so once again, we start with this model, you know, with the model over there. Okay, I have my feet completely tangled in, you know, wires here. Okay, so this is the basic, this is the model that I've shown you. We re-express it in terms of equalities, and of course we transform the max into a min. Okay, so we get these constraints over there. So we have two new variables, x3 and x4. Okay, very important, x3 and x4, because, you know, you'll see why in a moment. Okay, but see that we have x3 and x4, and you can express x3 in terms of x1 and x2, and x4 in terms of x1 and x2 as well. Okay, and now we are trying to do the tableau of this thing. Okay, so this is the tableau. Okay, so we see that at the beginning I put x3 and x4 in basis. Okay, so you see the value 1 over there, 1 over there. You see the b side on this side. You see minus z over there. Okay, and you see, you know, the objective function over there. Okay, so now what we are going to do is solve the linear relaxation. We are going to take this tableau and do the simplex algorithm of this tableau. And where we want to get is this point, obviously. That's geometrically where we want to go. Algebraically, this is what is giving you. Okay, so value 3 over 2. Okay, that's what we wanted to find. The two variables which are in basis are x1 and x2. Okay, so x1 is equal to 1. x2 is equal to 3.5. Okay, which is exactly the point. The algebra, you know, is the same as the geometry. Okay, we are happy. Okay, and then you look at this tableau, which is the tableau at the optimal value of the linear program, right? Okay, now you look at this tableau and you see that the variable x2 is actually given a fractional value. That's not good. Okay, so what you're going to do is take a cut, okay, a Gomory cut for that particular row of the tableau. Okay, so what the cut does, take the fractional part of every one of the coefficient, okay, and multiply that by the variables, the non-basic variables, and then take the fractional part of the b side, and so the fractional part of the sum of the fractional part of the coefficients have to be greater than the fractional part of the B side, okay? And you get this beautiful constraint, which is a quarter of x3 plus a quarter of x4 is greater or equal to 1/2, okay? And you look at that cut and you say, wow, what does it mean? Okay, and of course that's when I told you, that it's easy to re-express x3 and x4 in terms of x1 and x2. So we can take this cut and try to see what it means in the original space. So you're going to take the value of x3, which is in that system of equation, the value of x4, which is inside, can be re-expressed in terms of that system equation. You re-express these things here, and what you get is x2 is smaller or equal to 1. Okay, just massage this thing, okay, and you get x2 is smaller or equal to 1, which is what? Which is the first cut that I've shown you before. Okay, wow, that's great, right? So what I do is that essentially, when you do this Gomory, cut algorithm, you basically add these new constraints, okay, with the slack variables, okay. So you see the slack variables now, which is in the basis, okay? And you see obviously that the value here is minus 1/2, okay? So that's not good, that's not primal feasible. So you're gonna re-optimize using the dual simplex, okay? And then essentially what you will get to this point, of course, okay? And so this point corresponds to what? X1 is about 2/3, right? And x2 is equal to 1. Hopefully we get that in the tableau, and that's what we get, 2/3 for x1, x2 is equal to 1, okay? And we see once again the tableau, and the tableau is fine, except that when you look at the row for x1, x1 received the value 2/3, okay? So we have to generate a new cut, okay? So we generate a new Gomory cut, and this is going to be the cut, 2/3 of x4 plus 2/3 of s1 is greater than or equal to 2/3, okay? Now, you look at this thing and say, how did he get the value 2/3 for x1, okay? So look at because this is a minus 1/3 over there, okay? Now, this is very simple, right? So minus 1/3, you run downwards. What is the largest integer value, which is, smaller than this? This is minus 1. So you take minus 1/3 minus minus 1, which is plus 1, and that gives you 2/3, okay? So that's how you get 2/3 for this particular constraint, okay? Now, once again, you have these beautiful constraints. You have no clue what it means, okay? It's 2/3 of x4 plus 2/3 of s1. These are one variables was a slack introduced at the beginning. The other one was a slack introduced by the cut, okay? The first cut. So what do they mean? Essentially, what do they mean when you basically transform, using the definition of these variables, when they were introduced, okay? It basically gives you the cut x1 minus x2 is greater than 0, okay? Which is this beautiful cut here that we saw before, okay? Now we re-optimize and we get the optimal solution to this MIP, which is going to be this beautiful point over there. It's all integer and we stop, okay? Now this algorithm was invented in 1958 by Gomory, okay? And obviously at that point it was considered as an amazing achievement, because essentially people think people had solved linear program, and that algorithm was telling them, no, you can essentially generalize that to integer program just by using these beautiful cuts, okay? Now one of the things that you have to see here is that this is in 1958, right? So this is before complexity theory was invented. Cook invented complexity theory, NP completeness in 70 or 70, well, I think 1970 or 72. Okay, so essentially what we know now is that the difference between linear programs and mixed integer program is a big gap, right? So this is the gap between polynomial time and NP completeness. So when you run this algorithm, what is happening? Okay, so what is happening is that you may generate potentially an exponential number of these cuts, right? Otherwise, these problems would be polynomial, okay? And so essentially, at that point, when people realized that, and also did a lot of computer experiments using this algorithm, they saw that the conversions of this algorithm can be really, really slow. And there were, some other issues as well. So at that point, this algorithm was mostly considered as a beautiful theoretical result, but not practical, okay? But science is like the linear relaxation. It has, it's very unpredictable, okay? And so what happened is that these cuts were actually completely revived in the 90s by, these people, so Egon Ballas, Sebastian Seria, and Gerard Cornujol, okay? And what they show is that you can actually use this Gomory cut inside a branch and bound algorithm. You have to be a little bit clever. You don't want to introduce them one at a time. You want to introduce all of them for the tableau at the same time. You also don't want to introduce them at every node. You skip some nodes and so on and so forth. And they show that they actually were the best. They were outperforming every existing algorithm at that point. Okay, no, that was the thesis, that was part of the thesis of Sebastian. And if you want to read more about this, it's very interesting. Just look at the article that Gerard Cornejol has written on this. So this is very interesting, right? So Gomory Cut were basically a really a major breakthrough. Then they become essentially a tiny theoretical interesting feature, and then they become essentially completely practical again, and they are essentially integrated in all the commercial software now for MIP solvers. Okay, of course you don't generate them, all of them, you only generate a subset of them, but essentially they are a big part of every commercial MIP system since Sebastian, Egon, and Gerard, and I don't know the first name of Natrash, but these people actually did this computational experiment. So once again, this is an interesting story here. The science is beautiful, but there is also a very interesting story personally, and the story of Gomory is very interesting. He, after having doing a lot of science, he went to IBM, became an IBM fellow. He revolutionized the way IBM did research, and then when he was at mandatory age for retirement, he went to the Sloan Foundation and revived and revolutionized the Sloan Foundation as well. So you should read about him. It's very interesting. And once again, what you saw today is very interesting science and a very interesting personal story at the same time. Thank you.